Hello again. Welcome to Control Talks. This is the second video of a series of videos regarding modeling. If you haven't seen the Laplace and transfer video, I recommend you to do it before continue to this one. In this video, we are going to start learning how to model some physical systems. It is impossible to learn how to model every system in a single class or even in a complete course. That's why in the control system courses, we focus on relatively simple systems, but for you to understand the main idea behind modeling. The mathematical models come from the physics that govern the system you are trying to model. All the systems considered here fall under the category of LTI systems. And as we learned in the previous video, we can represent models using a state space representation or transfer function representation. In this video, we will focus on the transfer function representation. But first, every time we start modeling a system, we need to consider the elements that conform the system, the variables of interest we are going to analyze, and of course, the physics laws behind these systems. So let's start with translating mechanical systems. That is systems that move back and forth in a straight line. There are three fundamental physical elements in this type of systems. Inertial elements, which in this case are going to be the masses. A mass will be drawn along with a coordinate system in which the mass moves. A force is generally acting on the mass. Since the force tends to move the mass in the direction of x, we can write force equals to mass times acceleration or mass times x double dot. That is the second derivative of the position x. The direction of the arrow will indicate the positive sense of the directions or forces involved. It is important to realize that the defined direction is arbitrary. We could just as easily define the direction in the opposite way, in which case the force will become negative. It is also important to say that the mass is an element that may store energy as its velocity changes. This becomes important in state space representation, so keep in mind this as we move forward. Another element is the linear translating spring. It is an element that is deformed in direct proportion to the amount of force applied. Ideal springs have no mass. In this diagram, the end of spring K is determined by the position specified by x. The position of x is 0 when no force is applied to it. This means that the spring is relaxed. If we apply a force to the spring to the right, the spring elongates by an amount delta x such that F will be equal to K delta x. Since the displacement x is defined to be 0 when the spring is relaxed, we can write only F equals Kx. If neither side of the spring is attached to a fixed reference, the situation is slightly more complex. The force on both ends of the spring must be equal in magnitude and opposite in direction. This way, there is no net force on the spring. If there was a net force, there will be infinite acceleration because the mass of our ideal spring is 0. Since the location of the spring is now x1 minus x2, we write F equals k times x1 minus x2. In this case, the force F increases as x1 increases, because an increase in x1 causes an elongation of the spring, but decreases as x2 increases, because increasing x2 shortens the spring. This is an example of superposition. Because the system is linear, the inputs x1 and x2 can be considered independently. As with the mass, the defined directions are arbitrary. We could have chosen directions as shown here, which results in an equation where x1 and x2 are added. Now, an increase in either increases the elongation and therefore the force. A spring also may store energy as its dimension changes. Another important element is the friction or damping element. In the context of linear system, friction is assumed to be viscous friction. This means that the force of the friction is assumed to be proportional to velocity, that is p times x dot. There are two distinct ways that friction will be shown, like this, or as a physical damping element like dashboats, snowbirds, or any damper element. Energy is not stored in friction elements. Instead, Heat is generated and released to the environment. The physical law behind these systems is the Newton's second law, that states that an object accelerates in the direction of an applied force, and that this acceleration is inversely proportional to the force, or the sum of the total forces is equal to the mass times the acceleration. The variables of interest of these systems are the positions, the velocities, and of course, accelerations. Now let's see an example. We want to obtain the mathematical model of this mass spring damper system, where the output is the position of the mass and the input is a force F. Also, we want to obtain its transfer function and be able to simulate the transient response of the position when a force is applied using the differential equation obtained. We can use Simulink or Scilab to model the system. So let's start. The first step is to define the output and input of the system. In this case, the input of our process is Fin of t, and the output is the position of the mass y of t. The second step is to draw the body diagram of the system. We have the input force Fin, which goes down, and because of that, there is a reaction force due to the spring that is going up. The direction of the arrow of y of t will indicate the positive sense of the directions or forces involved. Considering this, the sum of all the forces equal to mass times the second derivative of the position y of t is equal to minus the force due to the spring plus the input force Fin. The spring force can be converted to k times y of t. This is the differential equation that represents the mathematical model of this system. The third step is to obtain the transfer function. To do so, we need to Laplace transform the differential equation obtained in step 2 as follows. ms squared y of s equal to minus k y of s plus fin of s. We pass all the elements except the input to the left side, factorize y of s, and finally, solve for y of s divided by fin of s. This is our transfer function g of s. The output y of s can be obtained by multiplying the transfer function times the input fin of s. Okay, so we have the mathematical model and the transfer function. Now it's time to see how we can solve this equation using Simulink. This is the step 4. We know that the variable we want to find is the output response. In this case, it's the position of the mass y of t. And that the second derivative of the position is the acceleration, right? Well, the first thing we are going to do is to solve for the acceleration from the differential equation. This is the equation we are going to model in Simulink. If you look to the equation of the second derivative, this equation is composed by the sum of two elements. So we are going to draw a sum symbol with two inputs. The input number 2 is the input force, so we draw it, and the input number 1 is the result of multiplying minus k over m y of t. So where we can get y of t? Well, we know that the output of the sum block will be the second derivative of y of t. So what if we integrate it 2 times to obtain y of t? So now we have y of t, and we can multiply it to minus k over m and send it to the block sum. This is called a data flow graphical differential equation. Now let's go to Simulink and draw this data flow. Okay, so here I have MATLAB, and I'm going to open Simulink to create our differential equation. Here we go. We click in Create Model, and here is. Okay, so I'm going to full screen this. I'm going to click in Library Browser. So the first thing we need, I'm going to put is a sum block. So you can search the sum block in this box, but if you go to math operations, you can see that there is an add operator. So I'm going to drag this element here as one of the elements that we need. Here we go. Um, then also I'm going to need integration symbol. So in this case, I'm going to write here integration. And we have this integration. There are two, but basically are the same. They're in different boxes. Actually, it's hard, yeah, commonly used blocks and in the continuous integrator box, but these are the same. So I'm going to drag this one over here. If you look here, it indicates me the initial condition of my system. In this case, I'm going to leave the initial condition as default, which is 0. Later, we can play with this, but for now, I'm going to leave it as it is. And I'm going to copy one more integrator. Remember, we need to integrate 2 times because we have the second derivative of the position, and we need the position, which is the output, right? So what else I need? I need gain. So I'm going to look for it here, gain. Okay, this is the gain. I'm going to put it over here. With Control R, we can flip this symbol. So we press twice. So I think we almost have everything we need. I'm going to start connecting these 2 blocks, and this one I'm going to connect it here, and then I need the input. So here, first of all, I'm going to go to the browser library, and here I think it's in sources. In sources, we have a lot of kinds of inputs, signals. The most important signal that we have here, there is a ramp, there is a pull generator, there is a step. This step is the one that we are going to use the most in this course. So I'm going to drag this one here. And this will represent the force. Every time that we are doing this, we need to be careful and try to understand what the things means. I mean, in the physical reality, I would say. So in this case, I'm putting the force In of the equation as a step function. What it does, this block does. This block, what it do is it starts in an initial value and then goes to a high value, let's say, and it keeps that high value forever. If I double click here, we can see that I can control the step time. That means where the step will start, the initial value and the final value. So that's why it's called a step, right? Um, so in this case, I'm going to put here 10. 10, I guess, can be newtons. Okay. And that's it. Okay, so we need a way to look the results, right? So in the Simulink library browser, we can go to things, and in things we can find a lot of things to display or to um, plot the output we want. In this case, I'm going to use the scope. I'm going to put it here. And I'm going to join it this way. So now I think we are done. I'll put it here. So we can also plot more than one signals here. In this case, I'm going to add another input signal to try to plot the input. Okay. All right. So now the equation says we need to integrate 2 times. These are the 2 integrators, and then we need to multiply the output for minus k over m, right? In this case, we have 1. So the good thing of Simulink is that we can also put here variables. So I'm going to write minus m and operations. Minus m, no, sorry, it's minus k over m. And I'm going to put, okay. Okay, if you look here, a warning came up because Simulink doesn't find these 2 variables. Okay, these variables need to come from the workspace in MATLAB. Okay, so let's do it. Put OK here, or if you want, I'm going to change to the workspace this way. So here I can define k and m. So k can be 100. Okay, this is the constant of the spring, and I define also m as, I don't know, 50. Okay. So now if I come back here and I write again variables, you can see that it appears k as 100 as we define it here. We have k over m, and click here. So if I make a little bit bigger here, you can see these both letters. So now I think we are done. We have constructed our model. So let's run it to see what happens. So I'm going to run here. We'll run for 10 seconds. Remember, this is like I'm applying a force over the mass permanently, right? This is the step, the meaning of this step, and the transient response of that action is in this scope. So I double click here, and now I have the response. So if you, this blue line is the step, is the input FIN, and the yellow line is the way the output is responding when we apply a force in this way. Okay. Another thing that we can do, I mean, we can play with the different inputs that we can apply in this system. So let's go back to the example in the first video. In the first video, I told you that we applied an impulse response. An impulse response is just a signal that goes up and then goes down. It's just an instantaneous punch, right? So I want to to simulate that in this video as well. So let's do that. We don't have an impulse response in Simulink, but we can create one. And let me show you how I'm going to build an impulse response. So let me use now this sum block. This is another sum block. It's the same. I mean, it's summing two signals. So just a different representation. I'm going to double click here and I'm going to put a minus sign there. I'm going to disconnect this and connect it here. And I'm going to create another step signal and connect it here. Now, if I double click here, we said that this step will start at 1 second, right? And will have a final value of 10. So what I can do is to open this, and instead of the step time starts in 1, I can put that it starts in 0.5. Okay, no, sorry, in 1.5. So after the first one. So if you can see, at 1 second, we are going to have 10 going through the zoom block, but half second later, we are going to subtract that 10 from this step. So at the end, we are going to have only a square signal, if you will. Okay? It's like a representation of instantaneous points, instantaneous punch. So I'm going to connect it here. I'm going to also connect the input signal, and I'm going to click run again. Double click in the scope. So see, the first thing we can notice is that is the shape of the input signal, right? So as I was saying, first of all, the first step came in. So the signal goes to 10, but then half second later, the second step makes the signal to go down. So this is a representation of an impulse response, more or less. And is physically in our system is like an instantaneous punch in the mass, over the mass. So what will happen that the mass will start moving because we have that spring, right? And it will oscillate forever because we don't have any kind of friction. If we added a friction, if we add a friction in the system, probably you will see that this will become too damper, right? But in this case, we don't have any friction. Indeed, we can increase our time, click run again, and see that the oscillations goes forever. Another interesting thing that we can make here is to do not have an input signal. I mean, to don't have any force over the mass. So instead of having these steps here, we can add only a constant. Let me go back here. Okay, we can add a constant and put it 0 in the constant. Obviously, if I make this, let me get back to 10. If I make this and, oh, I forgot to connect here the signal, so let me connect it. Obviously, the signal will be 0, right? The yellow signal, which is the output, is over the blue line, so we don't have any movement over the mass, right? But what happens if I move the initial position of the mass? Remember that the output of this sum block is the acceleration of the mass. The output of this integrator is the velocity of the mass, and the output of this integrator is the position of the mass. So I can change the initial condition by double click here of this of the mass, right? Of the position of the mass. So instead of 0, I can put a 1, maybe. Just let's see what happens with a 1. The idea is to change the relaxed position of the mast. I mean, to have an initial position, and then this is like, it's going to be like taking the mass, move it one, whatever unit it is, move it one down or up. In this case, it will be down, right? Because we define the directions to be positive down. So it's going to be like take the mass, move 1 unit down, and then release the mass. That will be the effect that we want, or we need to analyze that effect. So I'm going to put it here, okay, and I'm going to click on run. Let's see what happens with the position. Okay, there you go. Okay, so if you look now, the position starts at 1, as I defined in the integrator block, and then we release the mass block, and it starts to move because we have that spring. Again, it will oscillate forever because we don't have any friction to stop it. Okay, so that's another interesting uh, thing to analyze. And as I was saying, we need to look to the physical effects, because at the end, this equation is representing a physical model, right? So we need to understand what we are doing to that physical object when we manipulate this equation. Okay, and I think that's all. Thank you very much for watching this video. Bye bye.